Okay. We are doing a problem that is connecting work and kinetic energy. So we're going to use some equations that we have used in the past and some that should be new. Okay. We'll start with a picture because that's always a great place to start. So we have our lovely pyramid, which I think I'm just going to draw one side of the pyramid just for the sake of simplifying things. But you know what a pyramid looks like. So for our pyramid, it has a height of 147 meters. Okay, and then they told us that this angle right here at the base is 52 degrees. Okay. And then we know we have a box on it that's, or not a box, a large rock that is sliding down the side of this under the force of gravity. So in order to calculate this, we need to remember a couple of things, which is that work net is equal to the net force times the displacement, and that work net is also equal to our change in kinetic energy. I wish my brain didn't go like way faster than my finger, and I always write things out of order.
I do it when I type or reread my sentences, and then I'll skip like will and the.
Yes.
And when does that connect everything else?
So the nice thing about this problem is that they tell us in the problem that the rock begins at the top of the pyramid at rest. And moving objects don't have kinetic energy. So that means that when we're looking at change in kinetic energy, which is usually kinetic energy final minus kinetic energy initial, our initial kinetic energy is 0.
So it's basically just kinetic energy final is what our change in kinetic energy.
Yes, that is exactly it. It means that work net is not just equal to change in kinetic energy, but work net is also, in this case, equal to kinetic energy final, which is what they want us to solve for. So by taking these two equations up here and equating them to each other, we can get an equation that will give us a starting point for our problem. Take a moment to just erase everything here. And the equation we're going to be working based off of today is that kinetic energy final is equal to the net force times the displacement of the object. Okay, so we have to find our displacement and we have to find our net force in order to do this. Our displacement is just going to be this hypotenuse leg of our pyramid, which if we use our understanding of trigonometry, so we can use our understanding of trigonometry to solve for the hypotenuse. So we would say sine of 52 is equal to our 147 leg over x. And then if you manipulate that around, you could also write this as the displacement is equal to the height divided by the sine of theta. Then, in order to find our net force, which we only want the net force that is contributing to the displacement, which is the horizontal component of it, we need to find, so force net is going to be equal to the force of gravity, but the component that's in the horizontal direction. So I'm going to write force of gravity horizontal minus the force of kinetic friction that is opposing this. And they gave us our coefficient of kinetic friction, so we can use that and the normal force, which we can figure out from our diagram, to solve for the force of kinetic friction and then subtract it from the component of the force of gravity that's traveling in the horizontal direction. All right, so now we have our basic setup and we can move into more of the nitty-gritty. So if we do in fact solve for the displacement, what do we wind up with as our number value? Yeah, so displacement comes out to 186.555, something like that, and that's going to be in meters. Okay, so we'll just keep that number in our brains for later when we need it in our grand scheme of things. Okay. And we're going to work on solving for the net force. So I'm going to wipe the screen and redraw our diagram, and we'll try for net force. Aren't multi-step physics problems so much fun?
So much fun. It's just like the multi-step and the problems.
Okay. Oh, and our 147? Okay. So, in our box, gravity is technically pulling down this direction. But if we break this into its components, we'll have two components. We'll have one component that is perpendicular to the plane that the object is on, and then one component that is horizontal. We want this horizontal component. Through trigonometry, we can figure out that this angle right here is 52 degrees as well. So what that means is that our vertical component would then be cosine, because it's adjacent, and our horizontal component is going to be sine, because it is opposite the angle. And then we just take the cosine of the angle times the force due to gravity, which we know to be mass times acceleration. And we were given a mass, and we know the acceleration in this case is due to gravity. Right, so the mass that they gave us was 1.34 times 10 to the 4th kilograms times the acceleration due to gravity, which is 9.81 meters per second squared. And that will give us our force due to gravity, which we can then break into its component pieces using sine and cosine.
So that was the step that I was missing, was breaking it out.
Yes, the step we got stuck on was that we needed to break this into its components, and we were having trouble with the trigonometry of breaking it into its components. So once I realized that force of gravity could be broken down into a component that was horizontal and a component that was perpendicular to the surface, that is when it clicked for my brain. So we can do the math now if we want to. Okay, so our if we do the math for this, what does it come out to? Let's do that quick. If we do this mass, the force of gravity is equal to 131,454, and that would be in newtons. This is kilograms. Then we are going to break that into its components. So the x component is the 131,454 times the sine of 52. What I wind up with there is 103,587, and then a bunch of decimals.
Yep.
And that would be in newtons. Okay, so that is our force in the horizontal direction due to gravity. We need to find our force of kinetic friction to subtract from that number, so keep that number somewhere because we're going to need it again. And our force of kinetic friction is going to be the normal force times our coefficient of static friction, right? I was right. I don't know why I doubted myself. So,
Surprisingly, I got that answer without knowing that I got that answer.
really? It's like in your math?
All of those steps. But I couldn't connect why I knew to do those.
Hey, you there? You're getting there. So, our normal force is going to be is going to be equal in magnitude to the force or the component of the force of gravity that's perpendicular to the surface. So in this case, it would be cosine times this lovely number here.
Yeah.
So if we, I'll just wipe the page and we'll do that because you have our data for us. So we're going to take that 131,454 times the cosine of 52. So we'll get that answer. So then we come out with 80,931 and a bunch of decimal places, which I like to keep as many as I can just for significant figures later on. So that'll be newtons. So that's our normal force, which we then need to take times the coefficient of static friction or kinetic friction, which they gave us, which was 0.45. So if we take that times 0.45, we wind up with 36,419 and a bunch of decimals. And this is our force of kinetic friction. So we are going to then take the number that we got for the horizontal force due to gravity, which was 108 or something like that. 103. So it was 103,587 and a bunch of decimal places, minus this 36,419 and a bunch of decimal places. So what that comes out to is we wind up with 67,168.14199. Does that match up to what you got? So this that we've solved for right here is our lovely net force. But unfortunately, we're still not done. Because if you'll recall, we need to take that lovely net force, and I'm going to go ahead and clear my screen again, and we need to multiply it by the displacement that we measure, or that we calculated at the beginning, which was 186.5 meters, and this will be in Newton. 0.55. There we go. We'll keep the decimal points. So if we do that, then we should wind up with 12,530,216.889,122, and this is going to be in Newton meters, otherwise known as joules. So we look back up at all of our numbers from above, you'll notice that this needs to be in two significant figures, and I find the best way to do that is to put it into scientific notation. So I am going to go with 1.3, because you'll look here and notice this is a 5, so 1.3 3 times 10 to the 7 joules. And voila!
Explains why my answer was so close. Because
So all of that as a very complicated way of saying that you can calculate net force and displacement, and if the net force is only the net force that causes the displacement, you can calculate work, which is the same as the change in kinetic energy, so you can calculate the kinetic energy. Woohoo! All right. That should end kinetic energy for us. Now we're going to move on to the next section of the notes, which is all about potential energy. Potential energy is the energy associated with an object that has potential to move, hence the name potential energy. It has the potential to move. So, based on that, you're going to see potential energy in places where energy is being stored, basically. It's got this energy. It's not moving, but it has the potential to move, so it has this stored energy. And that comes either relative to its position to another location, or sometimes, based on its position to another location, or like tension stored in a spring, things like that. Potential energy, unlike kinetic energy, which depended on mass and velocity, which are both properties of the object, potential energy depends on properties of the object and how that object is interacting with its environment. So, it's not an isolated thing. We'll start by discussing the most common type of potential energy that you will hear people talk about, and that is gravitational potential energy.
what is it? Gravity always?
Yes. So unless you are on the surface of the Earth, you have potential energy of some kind. And as we're going to see as we talk about gravitational potential energy, what you define as your zero or your rest point helps, it will change how you calculate a problem. So gravitational potential energy is the energy associated with an object due to the object's position relative to a gravitational source. Here on Earth, relative to Earth, because Earth is the source of our gravity, being the most massive object anywhere near us. So, we calculate kinetic energy, or not kinetic energy, now my brain's stuck on kinetic. We calculate potential energy using this equation. And in this equation, m is the mass of the object, g is free fall acceleration, 9.81 meters per second squared, and then this is constant for objects near the surface of the Earth. So as long as you're, within our atmosphere, this should be your acceleration. And then h is going to be your height. And this is where it's going to become important that you define your height. So your height is measured to an arbitrary point that we would call your 0 point. Your 0 is going to be the point at which you say that object no longer has potential energy. So if I'm saying, let's say we have a 2-story building next to a 1-story building, and then we have the surface of the ground, right? If I say that the 0 point is the top of the 1-story building, if I say that's where the ball has 0 potential energy, then the height would be the distance from the top of the 1-story building to the top of the 2-story building. But if I say my 0 point is the ground, then the height would be from the ground to the top of the 2-story building. So you can see how defining your 0 point differently will give you different answers in your calculation. The fortunate thing is that most problems are going to give you some sort of indication as to what you should be setting your 0 point as. So when you get an example problem or a homework problem, it should tell you, or it should be obvious what you should be setting as your 0 point and how you should be measuring your height. Gravitational potential energy is not the only type of potential energy. There's also something called elastic potential energy. Elastic potential energy is energy stored in any object, like elastic object, that can be deformed.
So like a spring?
Yes. Or a rubber band. Or the surface of a rubber ball that you can push in and it bounces back.
So like just like a regular ball?
Mm-hmm. So anything that can be deformed and it will return to its original shape can store energy.
So like foam?
Mm-hmm. Some of them more than others, right?
Mm-hmm.
So compressing a string, stretching a rubber band, any of those can be considered elastic potential energy.
String?
Oh, I should say spring. It's a typo.
Okay. I was like, I guess you could consider that string is just multiple different ropes and that when you pull it, tie it, like you could
I mean,
technically just
some cords have elastic potential energy, but they're usually rubber ones. The amount of energy that is stored has to do with the distance that the object is either stretched or compressed from its resting state. And we calculate it using the equation potential energy elastic is equal to 1/2 kx squared. And in this case, k is what is known as the spring constant. This is going to be a small number if the object is really easy to compress or stretch, and it'll be a much larger number if it's a very stiff object that's harder to compress or stretch. And then it has a unit of Newton meters on it. And x is the distance that you compress or stretch the object from resting position. Here comes the example question. Okay, example problem. We have a 70-kilogram stuntman. He's attached to a bungee cord. And the unstretched length of the bungee cord is 15 meters. When he jumps off a bridge that's 50 meters from the ground, and when he finally stops, presumably before he hits the ground,
Hopefully.
the cord has stretched a length of 44 meters. Okay, so that makes sense. So he's a little bit off the ground still.
6 meters.
And we're going to treat him like he's a point mass. So we're going to disregard the fact that his mass is probably not all centered in the very center of him.
We're gonna make him a ball.
Yes, we're going to do what physicists do. And we're going to oversimplify, and he's going to become a ball. And we're going to disregard the mass of the bungee cord. It probably has a mass. It's negligible compared to the rest of what we're doing. Assuming the spring constant of the bungee cord is 71.8 Newton meters, what's the total potential energy relative to the water when the man stops falling? So they want us to calculate elastic potential energy and gravitational potential energy and add them together.
So wouldn't our point of zero technically be the 44 meters instead of 50?
Our point of zero will still be the ground for the gravitational potential energy. So if he's fallen 44 meters from a height of 50, the difference between those two will tell us how far he still is off the ground to calculate his actual potential energy at that moment. So let's draw a picture. Pictures are great. All right. I'm going to grab a new white background and draw our lovely picture. So we've got our suspension bridge. I'm just making this up. I don't know what kind of bridge it would be. And there's water underneath, and the very dumb man jumped himself off. And so this distance here is 50 meters. He stretched to 44 meters. The original length of this bungee cord was 15 meters. And then his mass, they said, was 70 kilograms. So the equations that we're going to want basically is that our potential energy total is going to be equal to potential energy of gravity plus potential energy. Why did it do that? Energy, and we're going to say elastic. So you'll need those equations of the potential energy of gravity is equal to mass times gravity times height, and then potential energy elastic is equal to 1/2 kx squared. Okay, you give this a shot and then we'll run it. Height would be this distance. So the distance that he is above your 0 level from the, so 6. Mm-hmm. So if we run this, I'm just going to clear the screen for us. Okay, if we run this, we should do the potential energy from gravity, which would be the mass, which is 70 kilograms, times the acceleration due to gravity, times the height, which is 6 meters. And that comes out to basically 4.1 times 10 to the 3rd joules. And then if we do the potential energy elastic, we should be taking 1/2 times the constant they gave us, which is 71.8 Newton meters. That is 2 M's. Newton meters. Then times our difference between 15 and 44, which will give you how far it's stretched, which should come out to 29 meters squared. There's a decimal point in there. And that, if you run out all those calculations, should come out to about 3.02 times 10 to the 4th joules. So then if you combine them together, you should get in the neighborhood of 3.43 times 10 to the 4th joules.
Yay!
You did it! Woo!
I do have a question. So how would you find the K? Spring if it was not
They, thus far that I've read in the book, they don't expect you to solve for K. K is kind of like it's not quite like mu, because mu was something we could solve for, right? It's more like
kind of like gravity, it will always
yeah.
be given.
Right, they're going to give it to you. They're going to say, like, this is, because every single object that you have is going to have a different one. Mm-hmm. And I'm guessing it's much more complicated to calculate than the scope of what we're going to learn in high school physics.
Probably physics, like college.
Yes. Yeah. Post-secondary. Yeah. All right. I do believe, if I'm not mistaken, that is the end of our notes.